Hello guys, welcome to the channel. Now let's see uh, MTI improvement factor. So here the clutter, basically the clutter attenuation can be made infinite by turning off the radar receiver. However, it would eliminate the desired moving target echo signals. So previously we have seen that this MTI, this is a clutter attenuator that we found for different delay lines, to double delay line and single delay line. So basically we need this attenuation to be very high. To make, for example, let us have an ideal case where we want it to be infinite. We can achieve that by turning off the radar receiver. But if you turn off the receiver, what will happen? The no signal will coming in and we can't detect the desired target also, right? So that's what, to avoid that problem of increasing clutter attenuation at the to avoid the problem of increasing clutter attenuation at the expense of desired signals. So basically what it means, if you want basically the first statement says that if you want to increase the clutter attenuation, we need to lose the desired signal. So to avoid that problem, a measure of performance known as MTI improvement factor is defined. MTI, basically moving target indicator improvement factor. So desired to factor is in, improvement factor includes the signal gain as well as the clutter attenuation. So basically it can be defined as the ratio of the signal output signal to clutter ratio to input signal to clutter ratio at FT. That means at the frequency of see, you can see that FT, right? The Doppler shift frequency. So when you write it in terms of like S naught as C out, and we rearrange it, and it is like C in by C out into S out by S in at FD. So C in by C out is called clutter attenuation, and S out by S in is called average gain. So here so that's what vertical line is, that we are finding this at the Doppler shift frequency. So the improvement of the factor can be expressed as the clutter attenuation CA is equals to C in by C out times the average filter gain. So basically that's what we mean by here, right? By multiplying clutter attenuation with the average gain, we'll get this improved factor IF. So the average filter gain is determined from the filter response H of F. So for the average gain for a single delay line cancel, because those are the filters only, right? So the single line delay canceller has a average gain of 2. For a double delay line cancellation of 6. Average gain is of 6. The improvement factor for single and double line cancellers are that IF for single line and double line. So IF for single delay line canceller is for lambda square by 8 pi square of this, and double line canceller is lambda power 4, like 128 pi power 4, like this. But here we can see in general what is the formula for n cascaded DLC, that means single, double, triple, like like n. So for n cascade so improvement factor for n cascaded double line delay line canceller is approximately equal to 2 power n by n factorial of 1 by 2 pi into sigma c by fp whole power 2n. Okay, so this is the graph between the clutter spectral width by spectral width, in the sense this width what we have seen, that shaded region. So is the width and there is a width, right? So that width per radial radar PR, pulse repetition frequency, and we are plotting against the improved factor IF. So n pulse delay line canceller. So double delay line canceller to 3 pulse canceller. So basically here we are seeing so here we are only cancelling out for 2 signals, right? Here is recording, yeah. So in this double delay line canceller to 3 pulse canceller, we can see delayed line here what happens, the input is given to one of the delay and the other is directly taken, and we are subtracting the same way that where we had as I shown in the start at the previous video. I have told you about delay line canceller, right? Single delay line canceller, where there will be one delay and there is the input signal. One will be sent into the delay, and the delay output is compared with the original input, and that like that. So it is once it is compared, that is single line. We are talking about double, so the again this output is done the same way. Again it is sent to another delay and the original signal will be compared with that. Okay, now double delay. So basically if for example if the input is s of t, the s of t is sent into this delay, that means it will be s of t plus tp. So the difference output is sent here, that is this one, the first delay line, s of t minus s of t plus t, and this output is then sent here, right? This entire output is compared with, that means entire output of this first stage or this first stage is subtracted with the input of the second, that is output of the second of this block, so here the block, what is the value here, this minus the delay is you need to apply tp, right? S of tp minus s of t plus 1. So this term will be coming coming at this wire. Okay, coming at this wire, and this value will be coming at this wire. Okay, now this entire thing will be the output of this double line delay. So how can we change this? Here we are using two different we are using two subtractors, right? Instead of using two subtractors, we can use, basically we can use, they are called summers. Okay, but they will do basically depending on the sign of the signals, they will be subtracted like that. So there is another so what we can do, we can achieve the same thing for using a single subtractor, where comparator basically where that is like, so that we call it as 3 pulse canceller. Okay, when use this, so basically we are changing this to this, but we'll get the same result. So how to get the same result? The first line, if you observe, it is st minus st, that means we should directly get this st right here. Yes, that st line we got. Next we should be subtracted with 1 time s of minus 1 times s of t plus tp. So what happened, wait, so wait, we can understand here. Actually it is not here, it is not still simplified. So when we simplify this, it will be like s of t minus 2 times, I'll write, wait, take this. Okay, so here when you simplify this is s of t minus, here one minus of st plus 1 and here also minus of st plus 1, that means minus 2 s of t plus tp, and here it is minus s of t plus 2 tp. This is the result of that delay output. So here, okay, after simplifying, now in this we can from this compare this circuit. I'll take this one also a screenshot. Okay, when you observe this diagram here, this is one is s of t, that is the directly we are taking the output, one of the, like basically see, we are having three terms, one is this, another is this. Basically we are using a summer, right? So basically what should do the values here, we can write this the same thing as s of t plus minus 2 of t plus tp plus minus 1, that is minus of t plus 2 tp. Okay, here basically this will add, and also as a gain, this line has a gain of so here it is a positive value, that's why it is plus 1. Okay, now coming to the second step, that is what, minus 2 s of t plus tp, the minus 2. So basically I will use a wire with a gain of minus 2. Okay, and this line has a gain of -2, and this s of t plus tp, right? This s of t plus tp is what, after passing through only one delay. That's why only one tp is there, not 2 tp, only one tp. That means it is after first delay line. So it will, here the value will be -2 times this delay. Okay, basically here it will be s of t plus tp, and here it will be s of t plus 2 tp, because it is passing through here and then it is passing through here. That's why the output here, basically output will say like, okay. So from here the s of t plus tp is multiplied with the line of -2. So we got this -2 into so -2 into s of t plus tp, and the third line is what here, that is plus I think it's yeah, sorry, it's a plus, because you will multiply this minus inside of this, right? So it will be plus only, sorry, my mistake. So basically again now this term has a positive value again, so +1 times s of t plus 2 tp, and we are adding all this. So that's what is happening here. Okay, 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 yeah. So this is what, how it is happening. The same way the triple delay line canceller to four pulse canceller. So in triple delay, like there will be 3 mod in triple delay, so there are 3 sets like this, same, it will be the same repetition. So 3 blocks which has all the gains plus or minus like that. Here it is -1 +1 -1 +1 -1 +1, because you need to subtract, no, you need to subtract this, like this minus this, this minus this minus this. That's why this line has gain of -1, this below line has a +1. So after solving all this, we got an expression of s of t -3 times this plus 3 times this -1 times this. So actually first s of t, so basically place an adder here, sigma, that is actually adder. So which has first we had a line of gain +1, and s of t is passing through over it, and it is passing through first delay. If it is a first delay, what should be the gain of that line? -3. So the line of this is -3. Now again, if it passes through the second 2 tp means at this point, right, after passing 2 delays, 2 tp, which has a gain of 3 plus 3, so 3 t plus 3, and after passing through 3 what you call 3 delays, and the gain is -1, so the line here is -1. That's what. And it is so why it is called 4 pulse canceller, because this is a canceller, like it's a comparator, let us take. So it is taking inputs of 4 wires, that means 4 pulses, right? Here it is taking 3. So that's what, triple delay line cancel to 4 pulse canceller. Okay, 3 delay lines, so 1 delay, 2 delay, 3 delay, these are delay lines. Okay, delay line, so it has 3 delay lines, we are changing it to 4 pulse. Okay, 4 pulse canceller. Now here also has 2 delay line, so this one and this one, 2 delay line, and we are changing to 3 pulse canceller. That's it. So basically there is another thing, the same model can be written like this also, transversal or non-recursive filter. Basically we are generalizing this in this way. So basically what happens, input will be given first, and that will be had some weight. In this case, what is the weight? 1 into s of t. So like that, the weight will be, maybe depending on the equation, corresponding respective weights we need to take proper weights. Weight in the sense the coefficients or the gain here, -1, -3, +1, these are called the weights. So like that. And the same if it is next term is what, for example, -3 s of, so this weight w2 will be -3, and like that with the time delay t1. So it is a generalized diagram with different time delays and different weights, and all these outputs are given to summer, we are getting the output. So transversal or non-recursive filters are MTI signal processing. Okay, the transversal filter is also known as a non-recursive filter, feed forward filter, finite impulse response filter, or FIR, for finite memory filter. So basically this is actually it's non-recursive and only forward paths are there, right? Only forward feed, no, there is no feedback, so that's why it is called feed forward filter, and also finite impulse response filter. So optimum MTR filter. So optimum MTI filter is a filter with so which maximizes the improvement factor. So basically this MTI filters will maximize the MTI factor. Uh, so basically optimum and normal. Okay, normal MTI filters are we'll get some normal value. When we use optimum MTI filters, we'll get better improvement factor than the previous MTI filters. Okay, it can also be considered as one which maximizes the clutter attenuation. So this optimum MTI filters will further increase the clutter attenuation than the normal MTI filters. So we can see a graph of frequency for with respect to amplitude response h of f, the like response of the filters. Okay, amplitude response of MTI delay line cancellers. First graph, that is the this smooth curve, is classical 3 pulse canceller. Second pulse represents the 5 pulse delay line canceller with optimum weights. Okay, and also 15. The third line is the 15 pulse Chebyshev design. So different models these are. So so now coming to the recursive filters. What are the recursive filters? Recursive filters have feedback also. We'll have feedback like this. Same process, but it also have the feedback. So these are also called infinite impulse filters. Okay, we'll see that. Wait. So infinite impulse response filters. So this is the diagram for a recursive filter, general normal diagram. It is called canonical configuration of a recursive delay line filter with both feedback and feed forward and feedback both. So when it comes to here, an input is given, so you can have feedbacks, right? When an input is given to this, there will be this input is going into this and it is traveling, and it is first taking the feedback here 0.04 some feedback, and they will be compared and the result will be sent here, and again it will taking the feedback from this. This is to our forward only, so see clearly. Okay, check and then only these are the feedback lines. This is a feedback line here. Okay, so shown in A is a recursive delay line filter with the frequency response. In B is the base of a 3-pole. Okay, based on 3-pole, zeros and poles are there. So like 3-pole Chebyshev design with 0.5 dB ripple in passband. This is a one filter that is okay. Now examples of frequency response of a recursive filter with 2 delay lines and a non-recursive filter with 4 delay lines. So for a recursive filter with feed weights are feed forward, recursive has feed forward and feedback, right? Both are good. So for a recursive filter, they have given the values of feed forward weights as 1, -2 and 1, and its feedback weights are 1, 1.561 and -0.641. That is for this graph. And the feed forward weights are for non-recursive filters are 1, this all 4. Okay, so basically you can observe there are totally 4 inputs here. Here in the recursive thing there are 2 delay lines, there are 2 feedback forward and 2 there are actually 3. So okay, sorry, 1 minute. So recursive 2 delay line and non-recursive 4 delay line. Okay. Filter design using zero. So basically filter design, so or filter which uses only zeros, you know, like poles and zeros of a filter response, those. So filters which use only zeros are designed under using zeros does not have the flexibility of the filters designed based on poles as well as zeros. So basically they lack the filters which are designed only using zeros lack flexibility when compared to filters designed based on both poles as well as zeros. Poles can be obtained with delay line cancellers by employing feedback. So poles we can get the poles by using this feedback. Basically, the feedback lines are generating the poles. If there is only feed forward, they will only have, they are called only zeros. They are all zeros. Okay, zeros are yeah. With both feedback and feed forward lines providing both poles and zeros, arbitrary filter frequency response functions can be synthesized from cascade delay times. Within the limits of reliability, these filters are known as recursive filters or infinite impulse response IIR filter. So when you use both feedback and feed forward, we'll call it as recursive filters or infinite impulse response. When you are only using feed forward, then it is called non-recursive or finite impulse response. Significantly, fewer delay lines are needed to achieve desirable frequency response function than with the non-recursive filters that only have zeros available for design in the jet plane. So significantly fewer delay lines. Basically, we'll require only fewer delay lines. Okay, while achieving the same desired frequency response, while then non-recursive thing. So we can see that here. Okay. So basically, for example, for a particular required frequency, if you use non-recursive system, it might take what wait, I will tell you that. See, I am actually, see, you can see here. So here we can see for we need a particular frequency response, but by using recursive filter we are only using 2 delay lines. But in the non-recursive filter we are using 4 delay lines. That means basically number of delay lines are reduced, right? For a when we use recursive filter. So that is the advantage, okay, of using recursive filters. I think it's 22. Yeah. And jet plane. So that's it. We'll see in the next class what is the staggered and all. We will see what is staggered pulse repetition frequencies in the next video. Thank you.